Hello, this is Arkaprava Saha. I'll be presenting a talk on my paper titled Shortest Paths and Centrality in Uncertain Networks. Many thanks to my co-authors Ruben, Yllka, Arijit, and Francesco. As we all know, a lot of real-world data is stored in the form of graphs. Now, that data can be uncertain for many reasons. For example, this figure shows a computer network, where nodes are computers and edges are cables connecting them. Sometimes the network looks like this, where all cables are available for communication. And sometimes it looks like this, where, as you see, some cables are not available because of network overload or technical faults. Motivated by this uncertainty in graph data, we can define uncertain graphs where edges have lengths as well as existence probabilities. This figure shows an example of such a graph. Now, we all know about shortest paths in deterministic graphs. If we were to extend this concept to uncertain graphs, one way is to use the shortest path considering only the edge lengths. However, such a path is useless if it is highly unlikely to exist. For instance, if such a path is used to transmit information from one computer to another in a network, then often the information will end up not reaching the destination at all. So to mitigate this issue, following the bulk of the literature, we adopt the concept of possible worlds, which are deterministic graphs obtained by independently sampling the edges with their respective probabilities. This figure shows an example of a possible world, where, as you see, some edges exist while the others don't. The probability of a possible world is the probability that all its edges exist and none of the others exist, as illustrated here. Continuing with the same example, we now demonstrate the concept of shortest path probability of a path in an uncertain graph. Suppose we are interested in the green path here. We consider all possible worlds where this path is shortest, which in this case are these 5 possible worlds, and compute their probabilities. The shortest path probability of this path is then defined as the sum of the above probabilities, as shown in the last line. We now state our problem. Given 2 nodes in an uncertain graph, find the path with the maximum shortest path probability. We call this path the MPSP, or the most probable shortest path. For example, in this graph, this green path turns out to be the MPSP from S to T, which is clearly not the shortest path considering only the edge lengths. We prove this problem to be sharply hard in our paper, and this is one of our contributions. This paper in WISE 2011 proposes a solution to this problem, which we use as our baseline. It runs in 2 phases. First, in phase 1, it computes paths in ascending order of lengths using Yen's algorithm till a stopping criterion is reached. For example, in the graph below, this green path is obtained first, then this, and finally this. These 3 constitute the candidate paths for the next phase. Now, if k prime paths are obtained, then the time complexity is as shown here. Next, in phase 2, it uses the Brokkelkamp algorithm to estimate the shortest path probabilities of the candidate paths. To do so, for every candidate P, it runs n rounds of Monte Carlo sampling. And in each round, it samples a possible world containing a random path P prime shorter than P. For example, say P prime is the green path. Now, if P prime is the shortest path in that sampled world, as shown in the figure on the left, the sampling round is said to be good, and otherwise bad, as in the figure on the right. Now, the fraction of good sampling rounds out of n is used to compute the estimate. Finally, of course, the candidate path with the largest such estimate is returned. Let's now discuss the shortcoming of this method. To recap, the time complexity of phase 1 is shown here. Now, in addition to mod v mod e being expensive, the number of candidate paths, which is k prime, turns out to be so large that this method does not finish in a reasonable time for most of our graphs. Going deeper into this issue, as we saw here, the true MPSP, which in this case is the green path, is enumerated only after all paths shorter than it, without considering the edge probabilities. Now, the number of such paths can be very large. So to mitigate this problem, we need to enumerate the MPSP in the candidate set quickly without enumerating all shorter paths. So what do? We use Dijkstra plus Monte Carlo in phase 1, while phase 2 remains the same, that is Brokkelkamp. Now, in our phase 1, we run m rounds of Dijkstra plus MC to generate the candidate paths. We demonstrate one such round with an example. Now, Dijkstra plus MC is similar to Dijkstra in deterministic graphs, except that when a node is reached, its outgoing edges are sampled with their respective probabilities, and only the sampled edges are used to decide the next node. So starting from S, given the outgoing edge probabilities, we are very likely to end up with this. Then we move to V, where again, given the outgoing edge probabilities, we are very likely to end up with this. Then we move to T. Now, lo and behold, we have a path from S to T. Now, note that since we use the edge probabilities to sample the edges, the MPSP is included in the candidate set very quickly, that is, for a very small value of M. This means that the time complexity, which is M times that of one Dijkstra plus MC round, is very small. Now, after the candidate paths are enumerated, we run the Brokkelkamp algorithm in phase 2 as demonstrated before. We now provide end-to-end accuracy guarantees of our method considering our 2 phases. Of course, we'd like to return the true MPSP P star with a high probability. First, if CP denotes set of candidates obtained by Dijkstra plus MC, then P star must be in CP, as otherwise it cannot be returned. This happens with a high probability as shown in the third line. And this implies that for a reasonably high shortest path probability, M needs to be very small, as we said just now. Even if P star is in CP, we also need to ensure that P star is the path finally returned. This also happens with a high probability as shown in the last line. We now show an application of our method to define a novel concept of betweenness centrality in uncertain graphs, as shown in this equation. It's analogous to that of betweenness in deterministic graphs, except that we use the set MGST, which is the set of MPSPs between S and T. Note that the summation needs to be across all node pairs, which is prohibitively expensive for large graphs. Hence, we need to sample node pairs to make it efficient. It can be shown that if the number of samples is at least a certain number, then with a high probability, the centrality estimate is very accurate for every node. Now, we empirically compare the performance of our solution to that of the baseline. As we said earlier, phase 1 of our baseline does not finish in a reasonable time for our datasets. Hence, to make the comparison feasible, we limit that time to C times that of phase 1 of our method, where C can take the values 0.1, 1, or 2. This gives 3 variants of the baseline, and we denote each by BLC. Now note that increasing the value of C leads to more candidate paths, and hence the solution quality, that is, the shortest path probability of the return path, cannot decrease. As performance metrics, we report the running time and the solution quality averaged over 100 queries. Our code is available here. As explained, BL2 is the best variant of the baseline in terms of solution quality. However, even that gets outperformed by our method, as shown in the figure on the left. Also, since the running time depends on the time threshold C, BL2 clearly takes longer than our method, as shown in the figure on the right. This shows the effectiveness and efficiency of our method. We now demonstrate a case study on brain networks of children as obtained from this project. A brain network can be modeled as an uncertain graph, where the nodes, the edges, the edge lengths, and the probabilities are as shown here. And this figure shows MPSPs in typical brains on the left and in autistic brains on the right. Notice, for example, that the pink path on the left is longer than the pink path on the right. This is consistent with various works in neuroscience which show that autistic brains are more closely connected than typical ones. This underlines the importance of our problem. So to conclude, we demonstrated a two-phase solution for finding the MPSP in uncertain graphs, which returns a very accurate solution with a high probability. We used it to define a novel betweenness centrality in uncertain graphs. Now in the future, it would be interesting to consider graphs where edge probabilities are correlated, or maybe to find the most probable densest subgraph in uncertain graphs. Thank you.